engaged in quantum computing research, and so I want to introduce the topic of quantum tomography. So in quantum computing, we store information using qubits rather than bits. So in classical computing, bits are stored in values of 0 or 1, but in quantum computing, those information is stored as a superposition of 0 and 1. And in this case, superposition means that rather than just being 0 or 1, a qubit can be 0 and 1 simultaneously. And the superposition is described by a probability distribution that represents what is the probability of getting 0 when you perform a measurement on the qubit. So in order to truly understand the quantum information you're looking at, you have to measure it multiple times, which is very different from classical computing, where you can just look up the value of a bit. Now, this presents a problem in quantum mechanics, where taking a measurement of a qubit is a destructive process that destroys the state. What this means is taking one measurement isn't enough to understand the state, but taking a measurement destroys it. And so the way you get around this process is with quantum tomography, which means you initialize the same exact state or the process that produced that same state multiple times so you can take that measurement each time. However, this can be really inefficient, as it means you can produce the same state over and over and over again, and you're just wasting time and wasting quantum resources when only a few measurements might suffice. So in canonical tomography, which is the traditional way of doing it, what they do is they use a frequentist approach where they just collect outcomes, and those outcomes that they see influence their values. Now, the issues with using a frequentist approach is that it can't estimate values for certain states that it hasn't yet encountered. And it also has no way of observing if the estimation process is going well or poorly. And by poorly, I mean you can get really unlucky and say a less probable outcome happens multiple times in a row. That would give you a skewed view of what your state is. You would think you might be looking at like a 50-50, 1 versus 0, when in fact your real state is actually 80-20. Now, in order to get around this unluckiness, in canonical tomography, they just overpower this with raw numbers. So they'll take 1,000 or 2,000 measurements, so that even if they are unlucky at some parts, it doesn't matter. They'll still get an accurate estimation of the state. Now, this is where I come in, and I introduced an adaptive tomography scheme. My adaptive tomography scheme tries, first off, it uses a Bayesian technique rather than a frequentist approach, which means I can estimate states that I have not encountered yet with measurement outcomes that I might not have encountered yet. And it gives me access to observe how well the state is performing as I take measurements. What this means is I don't have to take 1,000 measurements to overpower through unluckiness. I can observe when the state is converging at a specific point and then stop taking measurements at there, meaning I stop taking wasteful measurements of an information state I already know everything about. Additionally, the reason it's called an adaptive technique is because in canonical tomography, they have access to 3 measurement bases, and I just want to explain what a measurement basis is to you first. It means you're taking measurements from different angles of the quantum state. So what I want you to think about is if I'm taking pictures of you, because I want to know what you are, I can take pictures of you from this angle, or I can walk around behind you and take pictures, I can go on top of you and take pictures. It's the same idea. We rotate the state and we view it from different angles to try and understand what the superposition is. Now in canonical, they have access to 3 measurement bases, generally. They can have more, but generally they do it with 3. And they don't select which one will be next based on the outcomes that they're viewing. It's a preset. They take a certain amount of this, a certain amount of this, a certain amount of this. But the problem with doing that is they might have taken 20 images from this angle, and there's no point to take any more because they already know everything they need to know from this angle. They need to switch to a different view. My adaptive technique, it observes measurement outcomes as they come, and then switches the basis based on those adaptive outcomes. What this means is I'm picking bases that maximize the amount of information gained per measurement and moving away from measurement bases that are a waste of time. And in this way, I'm able to maximize the amount of information gained per measurement as compared to canonical tomography. So my adaptive technique, it's not just that it's more efficient in the sense that it gets more information per measurement than canonical, but because I can track the convergence of the state, I'm able to end early. I don't have to take uninformative measurements. And so if we look at what I've done, the canonical technique, all I do is I'm going to, well, first let me introduce this fidelity, okay? So fidelity is a quantity that defines how equal two states are. You're running it. How equal two states are. So if fidelity equals 1, that means that the two states are identical. And fidelity is a common use in tomography to track how well we're estimating the state. So what I do is I prepare a state in a canonical technique. I begin taking measurements, and I'm going to track when the fidelity reaches a 0.98. And by tracking it, I see that on average, it reaches that at around 150 measurements. But if you look at the range is from 12 to 300. This range is an example of the unluckiness versus luckiness of taking techniques. If we look at my adaptive one, I can see I converge at only 90 measurements, and that my range is much smaller, which means it's a lot more predictable. And that's because I'm able to track the convergence. Now this might, again, they're not actually going to take 150 measurements in canonical. They're going to take something like 2,000. Okay, but this is just displaying that my system is it's more efficient per measurement taken. Now the reason this is useful, like practically useful for the future of quantum computing, is it increases resource efficiency of your quantum resources and at the time it takes to do something. So if you have to take 1,000 measurements per quantum computation, so you can know what those computations are, versus having to only take 100 measurements, that means in the time that it would take you to do one computation, you can now do 10. You've effectively increased your power by 10 with a really simple, and this is really cheap. This is a simple, like, mathematical, statistical process of doing something that all tomography is already capable of doing, just using it in a way that's most efficient. And so you don't have to have a complex hardware that the modern quantum computers don't already have access to. Additionally, it increases the scalability. So I've been working with a single qubit state, but quantum states, as you add additional qubits to them, they grow exponentially. So it takes way more measurements to measure a 2-qubit state than it does a single qubit state, and even more to measure a 3rd qubit state. If you don't find an efficient way of doing this, in either case, this is going to balloon quite drastically, but in my case, I'm able to effectively make it more controllable, such that I can reach higher qubit numbers in a quantum state and still make it practical in order to take computations and take measurements with them. And so, yeah, that's what I've been researching.